the final tutorial in this session of basic review of basic things in physics, like doing graphs and doing calculations and so on, involves the building of a database. And this is really important because it's the way that you're going to convey information to your reader, in this case specifically me. So let's start from the ground up, and let's just, I'm going to build a database as I do on my software here. So first of all, in building a database, the idea here is that you're drawing a rectangle. Please make sure all sides are visible, that you don't use the edge of a page to represent an end. It has to be fully drawn in. Also, it's important to do your databases in landscape mode. It affords you a lot more room across, and many times you're going to have lots and lots of quantities. Now, I'm going to get you started on a simple database, one that we're going to be using actually, and you're going to be building when we do the next lab, or a lab, using this walking with uniform motion. Some of you in grade 12, if you're watching this, you've done this long already. Otherwise, this may be new to you. No matter what, here we go. So, the first thing we want to do is we want to just choose, and I'm just going to arbitrarily choose heading here. This is where we're going to have some headings that we're going to put in. And here is also where we're going to put some headings along the side, like so. What headings? Well, since we're talking about the lab involving walking with uniform motion, what I'm going to do is I'm actually going to draw a couple more in here. This will be for instantaneous time, and this will be for time interval. This will be for my instantaneous position, and this will be for my position interval or displacement. And this one will be for my velocity. So I'm going to pencil those in right now. So in this place spot here, we'll just kind of close that up. So, and here I'm going to put quantity. And here I'm going to put, what we're going to do here is we're going to have different things we're going to calculate. So, values. So what quantity we're looking at? Well, the first one I mentioned is instantaneous time. Symbolized by a single small letter T, whose units will be seconds. The next one comes from this, is derived from it, time interval, and it is delta T in units of seconds. So the time interval comes from the instantaneous time. Similarly, we have instantaneous position, and this is fit in this area here. Of course, you want to make it fit. D, you don't need a vector symbol in this case, and it will be in meters. This one will be, therefore, change in position, which is commonly referred to as displacement, and it's fine to just put displacement in there. You don't have to put it into position. But it's important, it's delta D, and it's also measured in meters, since the position is also measured in meters. And last but not least, this will be the average velocity. Now, in the case of perfectly uniform motion, average velocity is simply just the velocity, and the units in case will be meters per second. Notice, by the way, I just took this outside the chart. My units for fractional units are always meters over seconds. Please don't do this. That's not appropriate. Now what we need is we need some various pieces of data. So let's just choose here, well, 5 or 6, something like that. I may not go right to the end of the database, just since this is a Dakota. Now, all databases require a very specific title and should always begin with the word database, which you refer to in the chart. Database showing. And the idea here is that you are very clear and specific about what is showing. So it's showing, obviously, instantaneous time interval. So the title will be generally longer than you're used to doing. And it also has something to do with up here as well. So what we're going to do is we're going to now put in some values. Instantaneous time. We're going to start now. Since instantaneous time is at an instant in time, we don't put it in a square, we put it on a line representing this instant in time. So 0 seconds, 1.0 seconds, 2.0 seconds, 3.0 seconds, 5.0 seconds, 6.0 seconds, 4.3 seconds. So you notice once again on this line, these lines I'm indicating here. I'll just highlight one very quickly. This line, for example, this is the 4-second mark. It's an instant in time. Right? Now, your time interval simply refers to the time from your second time back to your earlier time. So the difference here is 1 second. Similarly, for the next one, it's from your later time to your earlier time. Once again, this time interval, and you don't need to draw these arrows in, I'm just doing that by way of example. 2 seconds minus 1 second is 1 second. 3 minus 2 is 1 second. And so you can see that the time interval, in this case, is 1 second. Right? Instantaneous position. Well, instantaneous position is where you're located at a specific point in time. So presumably, at the 0 second mark, you were at the 0 meter mark. Sometime later, you might have been at the 10.0 meter mark. At 2 seconds, you might have been at the 20 meter mark. Maybe at 3 seconds, you were at the 30 meter mark. I think you can see a trend or a pattern occurring. I'm making this one simple. 40, this is obviously uniform motion from our definition of uniform motion earlier. And at the 6 second mark, I'm at the 60 meter mark. What's my change in position? Well, this is important now. The change in position, displacement, is once again the difference between D2 and a D1. Another D2 and that D1. So in other words, it's always going from here to here, from here to here, from here to here, and so on. So 10 meters minus 0 meters is 10 meters. 20 minus 10. 20 meters minus 10 meters is 10 meters. 30 meters minus 20 meters is 10 meters. And so the pattern continues. So just to reiterate or review, your instantaneous position is always from the beginning. So you start here at the 0 meter mark and you go to here, and then you go to here, and then there. And you can see that your position is always getting bigger. The numbers are getting bigger, whereas your change in position is, for uniform motion, always stays the same. For every second I walk, I go 10 meters. 1 second, 10 meters. 1 second, 10 meters. 1 second, 10 meters. And so your average velocity, which of course is simply delta d over delta t, so 10 meters over 1 second is 10 meters per second. 10, 10, 10, 10, and 10. So we have constant velocity or uniform motion. And that is the way that you fill in a database of this nature. This is different than you're used to because now we're making use of these lines. We're not just always putting things in the space, we're actually putting things on the dividing lines because they represent an instant in time. An instant in time. This point here is the 0 second mark. This point is the 1 second mark. And if I was to actually put that on a number line, like so, let's just use a straight line. So if I was to put this on a straight line, then you might have something that looks like this. So this could be on the top, we could call this time, and down here we could call this position. And you would have different scales, obviously. This would be 0, 0, like this, so on. This is the 1 second mark, 2 second mark, 3 seconds, 4 seconds, 5 seconds, and stop right there, but it continues. Now, this is our position axis. So what we can do is we can designate whatever we want as long as we keep it consistent. So in this case for position, what I might want to do is I might want to let every one of these ticks be 10 meters. So 0, 10, 20, 30 meters, 40 meters, 50 meters. So if we use this as being east, you can say then at the 1 second mark I was 10 meters from home. This should be in meters, this should be in seconds. This would be at the 2 second mark, you're 20 meters from home. At the 3 second mark, you're 30 meters from home, and so on. Well, in order to actually get to the 10 meter mark in 1 second, to get to the 20 meter mark in 2 seconds, to get to the 30 meter mark in 3 seconds, you must be traveling at a rate of 10 meters every second. So again, every second you're going 10 meters, that's your velocity. Just one other point I want to make about this particular database. It turns out that for this database, you actually don't need this upper row due to the nature of this database. So what I'm going to do is I'm just going to change the property by making it white and making that white. And there we go. So that's what this particular database would look like. In some labs we do, there will be an upper one up here that will have the calculated values and so on and so forth, but this particular one, not so much. So this is what your database for walking with uniform motion will look like. And again, if you've already done this lab and you're aware of it, you probably remember it. So I'm hoping that this sheds some light, enlightens you, helps you, clarifies how to do a database in physics. Just a quick reiteration, always rectangles boxed in fully in landscape, and in this particular case we're actually using our dividing lines as places where we're going to put numbers because those represent instantaneous values as opposed to a range of values or a value that is over a range that occurs in the square.